selection. We're sorry because we determined last week, I think I had it on the board who's lecturing this week, but we didn't update Stellar until I did it this morning. But essentially I'm only doing today, and that's the last one on material selection for the model, and Wednesday is Dr. Jenkins, and then Thursday, Friday is
Steve Lyons.
Steve Lyons. And then next week, it's gonna be kind of similar, we're sort of repeating where I do all Mondays and then we switch over on Wednesdays. So this is, for me, a little bit of a challenging lecture because I'm trying today to bring everything together. We start saying, okay, we have something we want to build. We have an objective, we have a lot of constraints. We say we're going to compare metals and plastic and go a little bit deeper into their structure and how they behave. So we essentially done that. There were some pieces left last Wednesday about polymers that I'm going to continue on today, but I have quite a few examples. And the idea with these examples is really to show how in the end we end up selecting some of those materials. And a lot of times it is a big compromise between cost, the mechanical resistance, is it sufficiently strong, and then the environmental resistance, is it going to corrode or degrade over time when we're talking about structural materials. So we'll go over that, and again, there's a lot of reasons why we end up selecting a special material for a given application. I want to give you guys the idea. PVC is this, typically it's a white pipe. It doesn't mean because it's white that it's PVC, but most PVC pipes are white. They're used a lot for drainage. They're not used when you expect a lot of sun exposure because they do become brittle over time. So underground pipes is a typical example where you may want to use a PVC pipe. And this is an example of a belted spigot. So you essentially have one pipe that comes in with O-rings and it gets into the bell and it forms the seal. A big advantage of a design like this, this can be up to 10, 12 inches or small, 2 inches inside. One advantage is you can have a little bit of expansion and contraction, so it's going to allow for slip here. Because one disadvantage of the plastic over the metal is when you have temperature variation, you have more changes in strength, in length. So the thermal expansion coefficient can be, about 4, 5, 8 times more with the plastic than the metals. It has implication if you're looking at a system that has bed, which is most, building plumbing systems. So and this happened actually a number of times for very sophisticated kind of chemical lab or academic labs using biological substances. So if, say I have a few hundred of pipe in a building, and I'm just going to say 200 here, 200 feet of pipe, and then I'm trying to have these laterals that will go, say, to a lab, and then it's the drain for it, and then I have another lab, and it's the drain here. So in buildings, a lot of times you don't have these expansion systems by default. You can put them in. If you expect, say, you reduce the temperature, you run out of power, or something happens in the building, or you're in construction, and you don't have everything at a constant temperature, the length of that big pipe can vary by, say, 4 inches, or something of that order of magnitude if it's a plastic. And the implication here is if this little lateral is short and you try to move 4 inches, you get a lot of bending stresses at that transition, at those T's or Y or whatever the exact design is. So there are two ways around this. Is you can put an expansion joint on the main line here, and there are different kinds. You can make your main on purpose. You can say I'm going to make it in 2 segments or 3 segments. So you introduce a loop in it. and you fix it, say I fix it here, I fix it there, I fix it there. Now all of a sudden I only have 1 inch total, because it's gonna not move at these 3 locations and allow for having these short laterals. The other way is to have these segments being long enough that they will be able to take the tolerances. But this is something that is problematic. I've seen it even with metallic pipes. So even though we're not really, deciding whether we're using plastic or metals based on the expansion, it does have implication for how you end up doing the layout for your system. The other reason I was bringing this is we haven't talked a whole lot yet about what can happen during service, the usage factor, or say the anticipated abuse or overuse. So one of these situations with this type of design is you can push the pipe too far. And if you do, then you have the very end of the pipe here that's engaging with the plastic in a cone. And you can essentially force that plastic, this surface out, and it will crack over time. Now, if it was a perfect world, I think that I'd like to put a stop on the pipe so it's not possible to do this. One of the limitations with that is fabrication. To make a stop during the extrusion process that would really tag on there is not easy. You could weld something that the solvent cement weld, but it, up until I'm aware, it wasn't being done. And consequently, you essentially, with this type of design, you rely on, first of all, the pipe being cut square. So if it does rest here in this funnel or reduced diameter zone, reducing diameter, then it's going to contact all around and not at one spot. If it's contacting at one spot, then you can anticipate you're going to have a crack and leakage over time. So it's not the most bulletproof or system, and it's only used for normal drainage as opposed to very harsh chemicals or petroleum products. One of the issues that will happen specifically with PVC over time is this slow cracking, and that's going back to what we discussed last Wednesday. We said you can form crazes in the plastic. So you have these voids and you have the fibrils. So it looks like a crack, but it's not exactly a crack because they still have material. If you look at the very small upper image here, you still have material that's tying each side and preventing the opening, the further opening of the crack. What we're showing here is what happens if you apply cyclic load. So the N equal 100 or 200, 300, 450. This is what happens over time, and the bottom line is it's not a continuous process. So a lot of time you're going to form these crazes. They're going to continue to deteriorate, and if you remember from last time, you're going to have the molecular separation at the interface here. It's a very slow process, and the crack doesn't move. Now, when you reach a certain critical strength, it will move all at once. So that's called discontinuous crack growth. It will happen in Crete, so that's the constant load. If you were here last Wednesday, it will happen in cyclic load. It can also happen if you have an overload. So probably most of you have heard of fatigue, and that you can look at the fracture surface. If you see some lines, maybe there was fatigue. Now, in these examples, especially the upper one here, this all cracked at once. And the only reason why you see the lines is that the crack was stopping and continuing in steps. It takes time to break all these fibrils, but when you start breaking a row of them on the craze, they'll go right away and essentially exhaust it. And then you have this black zone where you don't have fibril, now you're blunting the crack again. It's going to stop there. You're going to grow another craze and it will propagate. So this is a typical way to crack in a material that will form crazes. I showed you some images of cracking in metals, if you remember, that was last Monday. So here we have it in relationship with the structure in polymers. So this is nylon here, polyamide, and what you see is essentially the center of the sterolite, and then this size is approximately the size of the sterolite. So you have one here, you have one there, you have one there. You can see them individually. They are of the order of about 10, 15 micrometers, a little bit like what we had for the metals. One special thing on this one, if you see, we're right in the center, and there's a little particle. So that particle was just, catalyst was just how the crystallization started in that polymer. I'm showing next to it an example of a nanocomposite. What happened here is you introduce the nanoclays, so they are about, the reason we call them nano is their thickness, but they're very small layers. So they're very cheap because you can exfoliate these layers from natural clay by chemical treatment. So you end up with something, because clay is a very layered structure. You have something of the order of a nanometer in thickness, but all these dimensions are more micrometers. So say we have 0.1 micrometer here, for example. It could grow bigger than that in that direction. So it's broken down from the natural clay product. The consequence of that is, if you have these particles and you manage to disperse them in the polymer, there's a lot of processes involved in making this happen. You have to functionalize the surface, essentially get some polymers to bond to it, so you don't have all the particles just agglomerating together. They stay separate, and they form a distribution in the melted polymer. So you have the melted polymer, and then you cool it down, it starts to crystallize, but here it's crystallizing from those surfaces, so instead of starting from a center, it's forming this more already kind of an oriented structure as opposed to the starting point. So this way of adding reinforcement actually changes also the crystallization of the nylon in this case. So it has a lot of, it causes improvement. If you put 2% of it, you can increase your yield strength by 60%. Just because now all of a sudden, instead of having your crystals oriented in all directions, and then having your slip plane at 45 degrees where you start easily to deform permanently, everything gets oriented and it grows perpendicular to the surface of the reinforcing particle. So you're increasing the short-term strength. Now, the reason I was bringing this example in is, well, one reason is I worked on it, so if you have more questions, definitely know more about it. But the other reason is, when we were talking about the creep of the polymers, if you remember, I said there is the movement of the chain segments over relatively short distances, so this is essentially rotating. When you have your carbon-carbon bonds, let's say you're like this, and then you have a side group here, so that side group can go to the other side, so you allow for some deformation, and that's the viscoelastic component. And then I said over a long period of time, you can have one chain completely moving with respect to the other, and that's more of a viscous flow. So what we're looking at here is essentially some specimens that were loaded in tension. It was cyclic load, but the effect would be similar if you use a constant load. It just goes faster. That's the advantage here. So you're looking at the amount of strain, and it's relatively small. We're only looking about 1–2% strain here, because nylon is relatively low viscoelasticity at ambient temperature. It's dry. This is essentially the rate at which the specimen gets longer. What happens during the experiment, you have a few material here, you have the material with the reinforcement, and then you have the material without the reinforcement. if we look at the one with the reinforcement, so the red is with reinforcement. At the beginning, it doesn't deform as much because you slow down the viscoelastic behavior, you increase the short-term strain. But what you find is after a certain point, when you reach this 10 to the minus 7th rate here per cycle, this is still relatively fast. These experiments were only a couple days long. What happens is your strain all of a sudden becomes constant. So this is I think, a good example of reaching viscous behavior, where now all of a sudden it doesn't matter how much strain you have, you're starting to have a strain rate that is constant over time. With the reinforcement and without the reinforcement under the same load, so this load is the same as this one. Over time, the material that doesn't have the reinforcement comes back to the same strain. And it's actually overcoming in here. You become at a lower rate of lengthening in the original polymer than in the composite. And that is because even though we managed to organize the crystals here and reduce the ability to deform easily at the beginning, we did not change, for example, the length of the polymer chains. These were actually set to be about the same for the purpose of comparison. And those are the ones that govern the very long-term behavior, this viscous flow of one chain with respect to the other. Now, it's not to say that molecular weight or the length of the chain is the only thing that matters for this long-term strain. If you have inclusions, if you have notches on the surface of the plastic or vented parts, that would be where the cracks start. And that, when we go to failure analysis later in my module, we'll go through more details about how to study the fracture and the cracking of materials. But here, essentially, there's enough evidence from looking at the entire specimen that the crack started at this point. The scale is 1 micrometer, so we're looking at a particle here that is of the order of 10, 15 micrometers in the entire section of the plastic. This was the biggest inclusion. Now, based on the chemistry of it, it was from the raw material. So essentially, as they process and try to clean these little clay particles, they had one that stayed unprocessed and caused the crack initiation. There's some other particles that are very small, so these actually are the nanoclays, but there's an impurity, and even though it's not on the surface, this was in the middle of the section, that's where the crack started. Very, very small. One of them, if you have a specimen with about this long, this big, one particle of 10, 15 micrometers where the cracks started. So it's these plastics are very sensitive to notch effects. If you reinforce it with small particles, so sometimes the cheapest plastic you can buy for sometimes toys will have a little bit of sand in it because it gives you a little bit more stiffness and it's extremely cheap. So you're essentially making a composite by adding particles, so you expense less polymer to make the part. But in terms of the cracking resistance, all these particles become sites where the crack can start. The other thing here that I want to point out is how fine all this microstructure is. These microvoids that were created, these are traces, and they were created very, very slowly. But they did involve, it's not because I see these traces, there's void formation that activate. This is the only thing that happens. So for the same material, what I want to show you here is an example where on the surface, you see all these fibrils. It's all very small ligaments. The reason it's white here, it's because it's at a very sharp angle. This is an electron microscope image. When you look at it on a cross section, so if you cut right through this material here, and now the little fibrils are on the surface, out of plane, what you see under the surface is a layer of deformation. This is material that is oriented. It's not like the material further back in the bulk of this polymer. So essentially it points to the first process taking place at the tip of the crack is plastic deformation, uniform deformation in the bulk that allows essentially for the large molecule to either go one way or the other, but again, they very rarely break. So they get sheared and moved from one side to the other, and you have the blunting of the crack. And somewhere in there, of course, you start forming voids, but it's not the only thing, again, that's taking place. There's just a lot of deformation. The reason or the conditions from which you, well, first, before we go through this, any questions on the polymer composite? Because this is being used. You can have it for some aircraft components, just little cushions or little appliances, because it's also more fire resistant. It's got much better permeation resistance, but in terms of structural application, it doesn't make the polymer all of a sudden the equivalent of a metal where it doesn't deform over time. It's still subject to this viscous flow over extended period of time. So it's not going to cause more mechanical reliability for long-term resistance. All right. So we started with PVC. We talked a little bit about nylon. And what I want to say is, if you know these two characteristics, if you know a little bit the size of the site group, which is this entanglement density, that's an index of that, and you have polyamide in the middle, we don't have PVC here, we do have polycarbonate. And you also know the temperature with respect to the glass transition temperature, and we'll go to that next. If you have those two characteristics of the polymer, you can determine whether it's going to mostly form shear deformation or if you're going to start to have craters. So it's not completely arbitrary. There's always an effect of temperature. So polyamide, which is right in the middle, depending sometimes on either temperature or moisture. Moisture will reduce the glass transition temperature, so it'll make the nylon softer and less likely to form craters than if it's dry. So those are the two main parameters that will allow you to know how it's actually going to deform. Now, the glass transition temperature is essentially an indication of where you have a very rate control, a very high damping of your behavior. If you have a liquid, it flows at a certain rate. If you have a solid that is rigid, it will behave like a spring. In this intermediate zone where you have the glass transition temperature, it's really in between, and you have a delayed response. That's a way to measure it. You essentially create an excitation. A lot of times it's just bending back and forth in the machine, a very small machine, so you can increase the temperature and look at that bending behavior over time. And you're looking at the delay in the signal for the cyclic deformation as opposed to the cyclic load you apply. And that is giving you essentially the tangent of the angle between the two phases, the excitation and the response. And that's how you know by the peak of that where the glass transition temperature is. In terms of the physics, what we look at typically is the volume of the material as a function of temperature. So let's put it the other way here. Temperature and volume. So if you do this experiment, what you'll see is there'll be a certain point where all of a sudden you have more volume. the macromolecular chains themselves, the amount of space they require, is a linear function of temperature for polymers. But you reach a certain point in the solid polymer where you start gaining more free volume. So this is the total volume, and this is the intrinsic, I'll call it. What happens is all of a sudden you have more free volume in the polymer. There's more void created, and of course that happens as you get closer to high temperature. And this is what allows you more easily to have all these viscoelastic deformation processes. So if you are very, very cold, you're a little bit like glass or a rigid polymer that won't have really much time dependency because there's no way for the molecular chains to move. But as you get closer to this temperature is where you start seeing the visco process, where if you give time, then all of a sudden everything becomes possible. So this is, I think, the more physics-based interpretation of the glass transition temperature. And if you have a polymer that will melt at a higher temperature, this point will typically move to the right. So you have PEEK, for example, that's used for relatively structural applications, based, but more expensive, but it has a higher glass transition temperature. So this process of knowing for a certain temperature how much free volume you have is the intrinsic behavior. Now, this is a very short-term experiment, but what you can do is by varying, these are all thermally activated processes. So the idea that if I'm at a certain temperature, say I'm right here, whether I'm going to be able to deform or not depends on the time that I allow for that deformation. So the time temperature equivalence process is essentially using this where for a certain temperature you change the rate of deformation, the rate of loading, or that cyclic load, and it gives you the equivalent behavior that you'll have. Say you go very fast at a low temperature, it's the equivalent of going slower at a higher temperature. So what people do with this is essentially accelerate the testing, where you have different experiment. You can do it here, for example, at different temperature, but for a short period of time, something that you can do here within a few hours. And use that data to generate what would happen over time if I had run the experiment much longer. It's a very nice process of analysis. It is based on the same viscous process continuing for all these conditions. So this superposition or equivalence doesn't allow you to predict the formation of crazes or the formation of shear bands of microvoids, because these become very localized processes and they're not just part of an overall bulk deformation behavior. So it's used, but it has a lot of limitation, and that's why ultimately you have to run, if last Wednesday I said a typical test will last about 3 months. If you want to know if your plastic pipe's going to last for 25 years. It's not something that you can do in just a couple of days, because you don't want to accelerate it to a point. This is huge acceleration. You're extrapolating over 6 orders of magnitude. It's not something that you can be sure that it's going to be the same mechanism of cracking. So I just want to summarize. We talked about the effect of whether we have a polycarbonate, a polyethylene, the side groups, and how they affect the behavior. The glass transition temperature is just an indication to relate us. When we know the glass transition temperature of a material, it relates to the structure and it tells us a little bit if the behavior we can expect between very ductile or the formation of crazes. The time temperature equivalence, you can use it to a different extent depending what you're trying to do. If all you're trying to do is to model the overall bulk deformation, you can use it extensively. If you're trying to look at the effect of what actually is going to cause crackers, then you're more limited. How the material is actually going to break a lot of times depend on the impurities that are in it, especially the polymers are very susceptible to the biggest flaw. If you have something that's being injection molded, like this component, if it's perfectly molded, a lot of times you have an orientation on the surface and it's more crack resistant than as soon as you break that skin layer, so that you have that natural orientation. And if you break it, if you machine plastics like nylon, you're not getting as much creep and fatigue resistance than if you use the raw molded product of the same, or microstructure, because of that orientation effect. So for structural applications, it's not easy to rely on polymers. We do it, as I mentioned, for the HDP, the polyethylene pipes for natural gas. We do it for drainage. We do it for potable water. I have some example here of cross-linked polyethylene, but it's not what is the most common. Now, you can make composites, and I won't go through the details. You can make composites of all sorts of kinds. We talked about metals. You can have a metal matrix composite, which are typically used for higher temperatures. The ones that we're more interested in the context of today's, you just put glass fibers. All of a sudden, if you remember the example of the underground storage tank, you just put these little particle chuck fibers, and then all of a sudden you increase the stiffness of the material. The composite will typically start breaking at the interface. So if I have fiber here, the first thing that's going to happen is I delaminate between the fiber and the resin, and then I start to crack through the resin, and then eventually I'll break the fibers as well. So that's what's shown here in this sequence of events of what happens over time or over the number of cycles. One advantage of, say, if you manage to have a fiberglass design or something where you have continuous fibers, carbon fibers, anything like this, is you have a lot of them. So if you just break one, typically it's okay. If you have a small crack in them, that crack can stop on its own. So what happens typically is they will not fail just because of mechanical excitation. They'll fail more because all of a sudden, I'm breaking all these interfaces, there's moisture penetrating, and the moisture is getting between the reinforcement particle and the matrix. That's a big problem, because now all of a sudden it's not connected together, it's a bunch of very strong fibers into a polymer. So you do need, essentially, it's not because you have fibers that you can let go the long-term resistance of the resin. And that's how a lot of industrial composites, so here you have pipe. If you remember pipe when we were talking about it, we said one problem with the unreinforced pipe is, so say I just had it here, is my hoop stress, so the stress going this way for pressure. So there's pressure inside. My stresses are twice as much around the circumference than they are in the longitudinal direction. So one way for industrial composite to work is you wind the reinforcement around the pipe, because that's really where you want the increase in strength. So this filament winding process, they'll use, say, plus or minus 15 degrees reinforcement. So it's really, it's easier to do. You form your core, and then you go and you start adding layers around, and then you put additional resin. So it would be easier, it's easier to fabricate. You can make these very complex fittings just by organizing how you're going to do this. But you still have to be chemically resistant because you need that interface, you need the resin to maintain its integrity. So that's the case all the time, and that's where the cost can vary a lot. You can have a resin that will allow you to make this pipe, but then all of a sudden 10 years down the road, if it's an acid environment, it becomes really, really soft, or it starts cracking, it's losing completely its integrity. So you have to still select based on the process. If you're going to put gasoline in it, it's different than if you're going to put water, because that resin needs to have different resistance to a solvent as opposed to water. It's very intricate, and I'm going to go on with this example where if you have plastic and it has certain properties, a lot of time there's antioxidants that are added on, and what they do is extend the life. So it's literally if you're aging wine, and you know, the wine gets better, and then eventually it turns to vinegar. There's a reaction taking place. So over here with the polymer, especially polyethylene, it's the same thing, where you put the resin, and a lot of time they'll have an antioxidant package. These formulas are proprietary, but what it does is these are very small molecules that diffuse through the bulk of the material, and they allow you to capture any chain breakage. So if there's a section of a chain, instead of creating a chain reaction where now you have more and more breaks, it encapsulates it. So the amount of that antioxidant that you put into your polymer in the first place when you manufacture it makes for the life of that polymer. So if you put a small amount, maybe you're going to resist the weather 1 or 2 days. If you put more, you can do 10 years. There are tests that are part of the standards, so starting next week we'll talk more about how we specify materials, and the test essentially for the antioxidant package, a lot of times you take a piece of polymer, you turn it into a pot, or you put it in the oven with a lot of oxygen, and you'll see until which temperature it's going to continue to hold its integrity as opposed to completely oxidize. And that is a qualitative index of how much antioxidant were put in it on the first place. So you can essentially make sure your manufacturing process is done consistently by taking that powder and heating it up slowly. And when you start seeing a reaction taking place, it means that you consume your antioxidant package, and you know either the amount of heat or the temperature which is taking place. So there's essentially a lot more than saying, well, I want high molecular weight polyethylene. There's the polymer, then there's essentially we talked about the viscosity of it, which is kind of a qualitative way to talk about molecular weight, how it's going to be processed, what kind of cooling rate, what kind of extrusion process, and then to resist the environment that you can have these antioxidant packages. We don't have them in PVC. I think the reason is that it's just hard to improve. So PVC will have a certain resistance, but it will pretty much be the same. Now, one way that you can improve, say, the resistance to X-ray from exterior exposure to the environment, we can put some small particle that will, like carbon black, that will just stop the penetration of the X-ray in the material, and therefore you are losing the strain at the very surface, but not in the core. So that is done quite a bit. If we try here to go back more generally speaking, so we have a few options. If you remember second class, I said we use a lot of steel and products because they're not expensive, and you can make them into a number of geometries. One thing you can do with steel a few things. If you can get sacrificial protection, we talked about the sacrificial anode, impressed current. A lot of times, essentially, you're creating a network of wires where you're gonna allow for a sacrificial piece or a permanent anode. It's either magnesium or zinc typically, or something more permanent. And then you relocalize, you reroute the corrosion process. Another way is to have this galvanizing, and that's very common on structures. You have beams outside that don't look painted, and they have a galvanizing on them to resist the environment. Now, the galvanizing is zinc with or without aluminum, and it will essentially be better than paint, because if you have a scratch that goes through it, you can expose the metal, but it's still protected. So you can have a little bit of rust, but it will still be protected. Now, every sacrificial system you have really only works if it's in contact with the environment. So this was a galvanized fitting that was galvanized inside and out, but the water, the interaction with the water on the inside is really what degraded over time, so you lost the galvanizing on the inside. You still have it on the outside, but it doesn't serve any purpose because it is not connected with the same water. If this was a pump and in closed position, it's submerged in water, it's not running, then you will have the zinc on the outside helping the surface on the inside, but it doesn't happen here. You'll see that there has been a little bit of a build-up. These are very small tubercles, but you can have them grow a lot bigger inside steel pipes. And a lot of times it will depend whether you're going to resist here with the galvanizing. This is just a bond wire, because what happens with the sacrificial system is you have to connect all your different metallic elements. So if you have a pump and you want to protect all the steel component, they have to be electrically connected. And this is just one for if you have piles. There was a big, the first Church of Christ Scientists on Mass Ave in Boston. They had wooden pile, and it's very typical for buildings in Boston, especially in Back Bay. They go all the way down to the rock. And they replaced them with steel piles, but they wanted to have long-term corrosion resistance of that steel. So we went on and put these sacrificial and impressed current, so catalytic protection system, but we had to connect every little piece of metal under the building together and apply a differential with respect to the sacrificial material. It's not easy. You have to essentially braze on steel, weld on steel to make the electrical law. Okay, so going back to the zinc here, the sample I'm circulating should have a zinc layer of any of those thicknesses. If it's hot dip galvanized, or if it's been an overlay process to create the zinc protective layer, it can be very thick. But if you look at the electroplated on the right-hand side, it's really, really thin. So if you say I'm going to use something galvanized, and then you go to Home Depot, and typically, unless it says it's hot dip galvanized, it's going to be the very thin galvanizing. You can expect a difference of a factor of 8 on the service life. So if a piece of plumbing fitting is put into service, and with hot dip galvanized we determine it will last 50 years, it makes sense that if somebody didn't use the hot dip galvanized and just used the electroplated, that it will only be 1/8, or it start failing after 6 or 7 or 8 years. And I have cases that are related just to that. Being in a submerged environment is when you can make use of all the galvanizing on the surface. We were talking that you can't use the galvanizing if it's internal corrosion, that you don't use what's on the outside. If it's weather-based corrosion, so here we have essentially cladding material, the base for putting the cladding is galvanized for building, And what you see is they just use self-drilling fastener to connect the siding to it, and just next to the hole made by these fasteners on the surface here, there's no galvanizing. You have the galvanizing here, but usually close to the surface, and there's only a distance of about 1/8 to 1/4 inch based on the size of a typical droplet of water, if you think of it, that will be still protected by the same environment. So when you localize your corrosion here, after you expense the zinc that is very close on one side, very close on the other, then you're going to start losing the integrity of your fastener. So it's a very problematic situation if you're thinking about the amount of zinc that's out there on the entire sheet is not what's going to be available to you to prevent the degradation and the tread from disconnecting over time. In this case, we lost the galvanizing over a distance of about 1/4 inch in only 2 years. So at that point, it was that they could have used, if we're thinking about 25, 50-year life, you could be thinking about, well, we may as well just put regular steel if the galvanizing is only going to last for the first few percent of the life. And the question is, did we need it or not for the application? Turns out they had a lot of condensation. This was a very sophisticated museum, and it was a very nice architecture, but there was a lot of humidity in the walls, and they had to eliminate that or replace the entire structural assembly. So in terms of material selection, a lot of times you'll think, especially with pumps, you'll have, say, an impeller that's going to be susceptible to perhaps a little bit of erosion if there's sand in the water. Then you're going to have some components that may have metal-to-metal contact. You have all the bearings and the bushing and all that. And then you have the main housing, which is really big and be expensive to make it out of a wear-resistant material. So pumps is a good example, or here the Liberty statue, where we do use dissimilar material. But when you put them into contact, you can have that galvanic effect, which depending on the situation, can compromise the function. A lot of times what happens if you're doing material selection is you want to avoid to have the small part being the one that's corroding easily. So it's okay, for example, typically to use stainless steel fasteners in a structure of regular steel, because if the stainless steel makes the regular steel corrodes a little bit more, it's okay, I have plenty of that, but I don't have a whole lot of that link. So that's an example. You can have, say, a copper roof where you don't want to use regular steel nails, even though the nicer to use, the stronger, because there's the small element, and if they're the most likely to corrode, you'll lose them very quickly. So there's a lot of basic decisions to make here in terms of your material selection, if you know they're going to be all in the same environment. So the idea of corrosion, and that was the topic I covered last fall in the discussion of coating, I think it was lecture 10 last fall. I went through the details, what exactly happens during the corrosion, but here I'm just trying to keep it in mind for you. If you have a corrosive environment, a lot of times people say, oh, I'll use stainless steel. But keep in mind that it's stainless, it's not stain-free, so it can still corrode and pit and lead to a degradation. In the ground, there'll be conditions where stainless steel doesn't do any better than regular steel. I really wanted to go through this example of a special pipe that utilizes multiple layers. I think we'll have to postpone that a little bit, but the idea here is if you want to avoid having oxygen in your system, the plumbing system, for example, that goes through a boiler, if you keep supplying oxygen into the boiler, you'll corrode the entire boiler. So you want to limit the intake of oxygen. And plastic doesn't do that, so this specific system here has multiple layers. You have plastic on the inside, and then you have an aluminum layer that's your oxygen barrier. So it's essentially another way to think, well, I really like the plastic, it's flexible, I can make joints easily, but I also need it to not be permeable to oxygen. So you add that layer, and that allows you to fulfill the extra function. Now, this may look really complicated to do. There's another view of it here. But can all be done as part of a single extrusion, a multiple extrusion process where you have the polymer coming in to make up the inside. You have the aluminum foil that gets overlaid and welded. So you have a little lap there on the aluminum layer, and then you put adhesive, you put the outside layer. In service, we've seen a lot of failure of these, and it's interesting because, of course, what happens is you fail the aluminum layer before it starts bursting. You can see a burst here on the outside. But what really happens is, this is the same material here. And what happens is it's the very inside part of the material that didn't have enough antioxidant. This is a whole production that went through a lot of homes, and they did not have enough antioxidant on the inside layer to be used with potable water. So this is a little bit where you start talking about, okay, I have this pipe and it will work well for a heating system, because the heating system, I have oxygen at the beginning and then I circulate and there's no more oxygen. But if I use potable water, there's always oxygen coming in, and then I'm going to degrade the polymer a lot faster. So I should have used the same quality of plastic that I used for a potable water line that doesn't have the aluminum layers. So the reason why it was used for potable water, it's not something necessarily the designer was thinking about, is you can bend these pipes with the aluminum and they stay bent as opposed to just coming back over time. So it's a lot easier to lay out your plumbing system. You don't need as much fitting. So people really liked it, but it wasn't built for those specifications where you have more oxygen than in radiant system. So,
And Kitech paid $250 million in lawsuit damages in Las Vegas alone.
So this ends our material selection module. I will send you an email. I'd like you to think about typical objectives of material selection and typical constraint. And maybe you'll say, I only have 3, I only have 1. It's not, but I want to follow up with that, and I'll respond to you if you do send me an email. Just a few lines. What you're thinking is typical. You can put them in order. This is just an exercise for you to try to sum this up as we move forward. And then next Monday, we're talking about material specification. Thank you.